everyone, my name is Marzi Haydari and I work alongside Hanping Zhang, Hao Yan, and my supervisor Yuhan Gu on this research. I'm excited to present our work on bilevel optimization for single domain generalization. Standard domain generalization usually assumes multiple source domains. That gives the model examples of domain variation during training. Single domain generalization removes that signal. We only have one source domain, so the model has to infer what is semantic and what is domain specific from a single distribution. Many SDG methods rely on augmentation, but this paper argues that target agnostic augmentation creates a lottery ticket dilemma. Performance is good when synthetic shifts resemble the target and poor when they do not. BiasDG addresses this by making domain variation explicit through surrogate domains and domain-never feature modulation. The key motivation is that the model has two coupled goals. First, the prediction model must learn task-relevant features. Second, the domain prompt encoder must learn useful domain-specific context. If these are optimized jointly with one flat objective, the prompt encoder can collapse into a trivial augmentation mechanism. Our paper explicitly noticed that joint optimization can become a naive data augmentation based model. So BiasDG separates the learning process. The inner loop optimizes the prediction model, the outer loop optimizes the domain prompt encoder for cross-domain generalization. Formally, we have one labeled source dataset. The prediction model is HOF, where F theta is the feature extractor and H phi is the classifier. The target distribution satisfies PT not equals PS, but PT is inaccessible during training, so this is not a domain adaptation. There is no target data, no target statistics, and no target calibration. BiasDG starts by creating surrogate domains. For each transformation pipeline at tau k, the kth surrogate domain is dk. The transformations are label preserving but domain altering. Color shift, texture shift, geometric distortion, photometric degradation, and similar changes. The important point is that these are not random isolated augmentations. They are grouped into coherent pipelines, so each surrogate domain represents a structured type of shift. For each surrogate domain, BiasDG estimates domain context from a batch. Here, if theta is a frozen or subgradient feature extractor and m omega is the domain prompt encoder. The outputs, gamma k and beta k, are modulation parameters that describe how features should be adjusted for this surrogate domain. The inner loop optimizes the prediction model parameters while keeping the prompt encoder fixed. The inner loss combines supervised cross-entropy and adversarial consistency. The cross-entropy term trains source domain classification. The adversarial KL term encourages local smoothness. Predictions should remain stable under small worst-case perturbations. So the inner loop asks, given the current prompt encoder, what task model performs best? The outer loop updates the prompt encoder. It evaluates the model after the inner update across all surrogate domains. This forces the prompt encoder to produce modulation signals that improve generalization across domain shift, not just source domain accuracy. The full bilevel problem is the minimizing the outer loss with respect to the inner loss. We propose to solve the bilevel optimization problem using stochastic gradient descent. The key for designing the optimization algorithm lies in deriving the gradient of the outer loss function regarding to the parameters of the prompt encoder. This will result in a second-order gradient. Although this is convenient to compute the first-order derivatives of the loss function, the second-order derivatives is not easy to compute. We hence further leverage a finite difference approximation method for the partial derivative. BiasDG is evaluated on digits, packs, and domain nets. On packs, BiasDG achieves the best average accuracy of 65.3% compared with 64.1% for ADVSD. On digits, BiasDG reaches 82.7% average accuracy compared with 80.1% for ADVSD. And thank you for your attention.